Okay, hi and welcome Chase to another video lesson. Today we're starting with chapter 6, which is differentiation. For the rest of the videos, because your exams are coming up, I'm really going to try and work as fast as I can. Hopefully squeeze in a few extra, like a few more than just 2 videos a week. But yeah, I'm going to do my best to get through this. So we're on chapter 6, which is differentiation, and we're talking about limits, which is the first section. Limits, which is section 6.1. Okay. So they talk about the concept of a limit. So here they show just a piece of the graph of y equals tan x or y equals tan theta. And this is 90 degrees here. Okay, so there's your graph of y equals tan theta. And basically what they're trying to show you is with tan theta in the previous sections we noted that as x increases or as theta increases, tan theta gets closer and closer and closer to this 90 degree line but never touches, and it just increases, it just keeps increasing up until 90. So if let's call this x. So if y equals tan x, right, and x tends to 90, so as x tends to 90 degrees, do you see that y just gets bigger and 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 carries on forever? So as x tends to 90 degrees, y tends to infinity. Okay, stated otherwise, the limit as x tends to infinity of f of x equals the limit as x tends to infinity of tan x, okay, which is equal to infinity. Because as we get closer, basically what the limit means is as x approaches, what is the value? So limit as x tends to infinity says what is the value of f of x as x gets closer and closer to infinity but never touches it? So, or in this case, as x tends to 90, sorry, as x tends to 90. So x tends to 90 degrees, so that's round about here. You see that tan just goes up and up and up and up to infinity. And that's why our answer is infinity. Okay, so example 1. Find the limit. It says find the limit of y equals 4 over x, which is a hyperbola, as x tends to infinity. So I'm going to write it out. They haven't. Limit as limit of f of x as x tends to infinity equals the limit of 4 over x as x tends to infinity. So here we're going to look at the first method. What they've done is they've plotted the graph. You don't always necessarily need to plot the graph, but if you can do it quickly, just a sketch, it does help. So there is just the positive piece, the first quadrant piece of your hyperbola, 4 over x. And notice as x increases towards infinity, right, what is happening to y? Well, it's going down, 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 closer and closer to 0, right? The y value is getting closer and closer and closer to 0. Okay? So, well, how they've illustrated it is they've done just a few calculations. So let's say at x equals 10, so we're just substituting x equals 10 in there, we've got 0.4. As x equals 100, you've got 0.04. As if x equals 1000, you've got 0.004, and eventually 4 over, when x gets to infinity, we have 0. How you can test this, essentially how you could test something like this on your calculator would be to say, you just substitute, if they say x tends to infinity, substitute into your calculator, just put in 4 over 9, 9, 9, 9, 9, 9. Do a couple of 9s, and you'll see that'll be equal to 0, approximately. So 4 over infinity is 0. So this is equal to 0. Okay. So then they give a couple of rules in your book. If a limit is to be determined, we do the following. Okay, step 1, sub value of limit. Okay, the value of the limit being this number here, in this case infinity. Sub the value of the limit directly into the equation. Okay. B, calculate the value. Okay. C, if we get infinity over infinity or 0 over 0, the result is meaningless, and we'll have to use a trick. Okay, and I'll teach you the tricks now. So these two cases are your problems, okay? And we'll teach you the tricks of how to solve that now. So once again, how do I evaluate a limit? I substitute the value of the limit directly into the function, okay? And then I calculate the value. So for example, things like 1 over infinity or infinity over 2. Those are fine because 1 over infinity is equal to 0. Infinity over 2 is equal to infinity. Okay? Because if you divide an infinite number by 2, you end up with an infinite number. Okay, so in any of those cases, you're fine. But if you end up with infinity over infinity or 0 over 0, your result is meaningless and you'll have to use a trick. A few other things I just want you to note. Infinity plus a is equal to infinity. Infinity minus a is equal to infinity. Infinity times infinity is equal to infinity. Okay? So infinity plus a constant stays infinity. Infinity minus a constant stays infinity. Infinity over a constant is equal to infinity. Infinity times a constant is equal to infinity. Right. And then we've got a constant over infinity. So a small number over an infinite number is equal to 0. And yeah, so those are just a couple of rules. So it's nowhere stated in your book, but just so that you know. These are important and you should understand. Okay. So in these cases, if you add or subtract a constant from an infinite number, it's basically irrelevant compared to the infinite number, and that's why infinity plus a or minus a is equal to infinity. And an infinite number times an infinite number gives you an infinite number. An infinite number divided by a constant is still an infinite number. An infinite number multiplied by a constant is still an infinite number. A constant, so 5, divided by an infinitely large number will be equal to 0. Okay, so here's your 3 steps. Substitute your limits in. Calculate the value. Okay. If you end up with infinity over infinity or 0 over 0, we will have to use a trick because that result is then meaningless. Okay. So let's just open a new page here. Right. So let's take a look. I'm quite glad we're finally into calculus. It's far more entertaining than trig. I hate trig. Okay, so let's look at example 2. Okay. They say if f of x is equal to 2x over x plus 1, determine the limit as x tends to infinity of f of x. Right. How are we going to do it? Well, follow the steps. The first step is substitute in. So this limit is equal to the limit as x tends to infinity of 2x over x plus 1, right? Okay, because now I've just put my function in here for f of x. So this is equal to 2, and now the limit falls away once you substitute in. So 2 times infinity over infinity plus 1. And you'll remember that I told you with our earlier rules that a constant times infinity is infinity over infinity plus 1 is infinity. Okay, you can review the rules that I gave you on the previous page. So we've got infinity over infinity. So this is meaningless. Okay, so we have to use a trick. Okay, and what are the tricks? What one of the tricks is to divide the numerator and the denominator by x. Okay, so our trick is divide numerator and denominator by x. Right, so let's do it. And because we're dividing by both the numerator and denominator by x, it's the same as multiplying by 1 over x over 1 over x. And you'll see that this is actually 1. So we can do it because we're just multiplying by 1. So it's not a problem. So let's quickly do it. So now we say f of x equals 1 over x times 2x over 1 over x times x plus 1, right? So you'll see that these two cancel out because it's just 1. So we haven't changed the equation in any way. So we can do it. So this is equal to 2x over x over x plus 1 over x. Okay. Which is then equal to 2x over x is 2 over x is 1 plus 1 over x. Right. Then, now that we've used our trick, we try evaluate the limit again. So, limit as x tends to infinity of 2 over 1 plus 1 over x. Okay? So we just start again. Now that we've got our function in a new form, we just start evaluating the limit again. So now we can just substitute in infinity. So that is equal to 2 over 1 plus 1 over infinity. Okay? 1 over infinity is a constant over infinity, and we've said that's equal to 0. So it's 2 over 1 plus 0. So 2 over 1. So the limit is 2. And there's your final answer. You've evaluated the limit. Okay. I also want, with your, remember I showed you rules for multiplication of infinity. I just also wanted to note a negative constant, for example, negative 1 times infinity is equal to negative infinity. So negative a times infinity equals negative infinity. Negative a times negative infinity equals infinity. Let's see, infinity over minus a equals negative infinity, and negative infinity over negative a equals positive infinity, sorry. So basically what I'm trying to tell you is that when you're working with infinity, the signs still apply as per usual. Okay. Next we're going to move on to example 3. You might want to pause the video and spend some time looking at those definitions there, these ones and the ones I put on the previous screen. Okay, example 3, because those aren't in your book, by the way. Example 3. Okay. They say consider the graph of y equals log 2x. Okay. So I'm just going to plot this. You can, so the graph is y equals log 2 of x. And I'm just going to sketch it here, but you can plot it on your calculator accurately if you want. It's not necessary. Basically what they're saying is, note that as x tends to 0, so if we look at x, as it goes to 0, do you see that the graph goes to negative infinity? Okay, so mathematically that is written as the limit as x tends to 0 of log 2x is equal to negative infinity. Because as x goes to 0, log 2x goes down to negative infinity. Okay, so what they're trying to show you here is note that x, with the limit x does not always go to infinity, it can tend to any number. Okay, so let's move on to another page. I'm burning through pages today apparently. Right, come on. Sometimes this thing doesn't want to move pages. It's very irritating. Okay, example 4. Example 4. Okay. So they give the example. Find the limit. Find the limit as a tends to 0 of x plus a squared minus x squared over a. Okay. Do direct substitution. As always, with our limits, you substitute in the limit value and see what happens. So this is equal to x plus, remember we're substituting in 0 for a. X plus 0 squared minus x squared over 0 is equal to x squared minus x squared over 0 is equal to 0 over 0, which is meaningless. 0 over 0 and 0 over 0 and infinity over infinity are meaningless expressions when it comes to limits. So we're going to have to use a trick. So for our trick, let's try multiplying out this bracket. Simplify this bracket, right? So that'll give us limit as a tends to 0 of x squared plus 2ax plus a squared minus x squared over a, right? X squared minus x squared cancels, and we've got the limit as a tends to 0 of 2ax plus a squared over a. See, now if we substituted a indirectly, you see we'd end up with 0 over 0. But what if we take out a common factor of a, which is there? So limit as a tends to 0 of, take out common factor of a, that gives 2x plus a over a, right? Those two cancel, and we're left with limit as a tends to 0 of 2x plus a. If we then substitute in, we're left with, we substitute in 0 for a and we're left with 2x. And there you go, you've evaluated your limit. So the trick that we applied here was factorize okay, and there you have it. Let's quickly take a look at, yeah, we can take a quick look at the last example. I'm going to squeeze it in here. So they say find the limit as x tends to 1 of x squared minus 1 over x minus 1. Okay, so what happens if we substitute in? Well, we're left with, so let's do it. It's a limit. We always try substitution. We're left with 1 minus 1 over 1 minus 1 equals 0 over 0. So that's obviously not going to work. Okay? That doesn't work. What if we try multiplying by 1 over x times 1 over x? So 1 over, so we take the limit as x tends to 1 of 1 over x times x squared minus 1 over x minus 1. That's 1 over x times 1 over x. Sorry, that's very messy. So that is equal to x minus 1 over x over 1 minus 1 over x. Okay, and limit x tends to 1. Okay, if we substitute in our x equals 1, we get 1 minus 1 over 1 minus 1, which is again 0 over 0. So we still need to use a different trick. Okay, so then we can try factorizing and multiplying out, which is our last trick. So the limit as x tends to 1 of x squared minus 1 over x minus 1. Okay, so let's factorize the top. Limit as x tends to 1. You need to carry that limit on the outside. So that is a difference of 2 squares. So we factorize x minus 1, x plus 1 over x minus 1. Okay, that cancels with that. And we're left with limit as x tends to 1 of x plus 1, x plus 1, and that is equal to 2. And there you have it, you've solved your limit. Okay, so in summary, when you're working with limits, first, try direct substitution. So substitute the limit value in for the variable. If it gives 0 over 0 or infinity over infinity, try your tricks, which are, number 2, divide numerator and denominator by x, so which is the same as multiplying by 1 over x over 1 over x, right? Okay, and then if that still gives a 0 over 0, infinity over infinity, you try your third trick, which is simplify and or factorize, and then you will get your answer, because that is all your syllabus covers. Okay, and that's the end of 6.1. Next we're going to go on to the gradient of a curve. Okay, so let's just open up a new page for ourselves here. And we're going to move on to section 6.2. 6.2, gradient of a curve. Okay, so this section basically gives you a curve, and they say consider this curve. It's a parabola. Okay, and they say find the gradient of a point, or find the gradient of the curve at point A. Okay, call this point A. Now if we draw a straight line between these 2 points, because it's a straight line, we can get the gradient easily. It's just m, and basically delta y over delta x, right? So that's using the tangent method. But that doesn't give us the gradient exactly at that point, okay? Because the gradient at A is actually a tangent line, let me do it in red, a tangent line that looks something like that. So we pick points A and B here, but that doesn't give an accurate description. What if we pick points A and B closer together? Well, point A is given. What if we pick point B here, right? B, that is a B. Okay, now if we draw a straight line through there, you see what we end up with, which is very close to that tangent line that I told you about. Okay? So, basically, the whole point of this gradient story is to select points A and B very, very, very close together. And when you do that, you can get the gradient very accurately using a straight line. So basically, your book gives a whole explanation, but we're in a hurry. The point is that the limit as delta x tends to 0 of delta y over delta x between 2 points, change in y over change in. So there's your delta y and delta x. Okay, so the limit as delta x tends to 0 of delta y over delta x is the gradient, equals m. Right? Okay. So, yeah, that is your equation, or that is where differentiation comes from. And I'm going to skip, there's a lot of nonsense in your book in section 6.2. It's not really that important. What is more important is 6.3, which is the alternative method to determine the gradient of a curve. So essentially, if I've got a curve, that same curve that we were looking at now, okay, and I just increase, so if I look at delta y over delta x between 2 points that are very close together, and let's call this x distance h, right, then I can find the gradient. So essentially there's a formula to it. Okay? Your book goes into explaining the formula. I'm not going to go there. I really don't think you'll be asked it. Basically the formula is gradient equals the limit as h tends to 0, so as I've made this gap between these 2 points very small, of f of x plus h minus f of x over h. Okay? So it's very simple. If they ask you to find the gradient of, let's say, and this formula is known as the first principles formula for differentiation. So if they say differentiate by first principles, they mean use this formula. So if I say find the gradient of y equals 2x squared by first principles, so by first principles, then we're just going to use this formula. So m equals the limit as h tends to 0 of f of x plus h minus f of x over h. Right. So now we substitute in. So f of x is 2x squared. F of x plus h is 2x plus h squared. So let's start substituting. So it's the limit as h tends to 0 of 2x plus h squared minus 2x squared over h. Now I can tell you when you're differentiating by first principles, you always need to multiply out this bracket. Okay, so this is equal to the limit as h tends to 0 of 2x squared plus 2x h plus 2h squared minus 2x squared over h. Minus 2x squared plus 2x squared cancels. And can you see we can take out a common factor of h here? So limit as h tends to 0 of h into 2x plus 2h over h. H and h cancels. It's the limit as h tends to 0 of 2x plus 2h, which is equal to 2x if I substitute 0 in for h. So there is your gradient. So m equals 2x. Okay, and that's how to differentiate by first principles. I'm really not going to go much further with this section. This is all you really need to know, is differentiating by first principles, and it's always the same. You know, use this formula, substitute correctly. You're going to end up with a bracket squared here. You need to, or whatever the case may be, you need to always multiply out this bracket. If it's cubed, whatever, you need to multiply it out. Then you're going to take out a common factor of h from the top, and then you're going to get your answer. Okay. Okay, the next section I see in your book is section 6.4, which is developing functions with the binomial. Okay, this section is basically how to use the binomial to write a function in a different way. And to be perfectly honest with you, I don't think it's worth our time learning it. It's quite complicated, it's quite long, and it's really not, in the bigger picture, it's not going to help you at all with differentiation. It's actually, yeah, it's a bit ridiculous. So personally, I vote we leave this out for now. If you see any questions in your exam that say, so just look in your past papers or whatever, is there anything that says develop this function with the binomial or something like that? If that is the case, we'll learn it, but if it hasn't come up in a past paper, I don't think it's worth us teaching. It's going to take quite a while, and it's probably not something you're going to remember very easily. The formula is quite complicated. So I think we're going to leave that out and move on to proper, not first principles differentiation. Okay? And that is section 6.5. Okay, so here they say that the function m equals limit as h tends to 0 of f of x plus h minus f of x over h is differentiation by first principles. Okay, so this is first principles. Principles. Okay, the next section that we're going to do is actually just called ordinary differentiation, and this is the easiest and best way to differentiate. First principles is just to teach you the concept, and that's it. So, ordinary differentiation. Okay. And we've been through this before with your assignment. And we're going to cover it again here nicely. This is the most important section in this ordinary differentiation, which is the rest of the chapter, is the way that you're going to do differentiation in general. Like, no one uses first principles to do differentiation. No one. It's just to teach you a concept at first principles. So unless it says explicitly use first principles, you're always going to do ordinary differentiation. And in the real world, if you ever use it, you are also going to only use ordinary differentiation. And ordinary differentiation is nice. It's much easier, and there's just a couple of rules, and if you understand the rules, then differentiation becomes a breeze. It just takes a while to catch on to. Okay, so we're talking about 6.5 here, chapter 6.5. And they say blah 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 blah. They give you a definition of differentiation, which I don't like. This differentiation, so they talk about, and this is on page 612, they talk about a definition of differentiation. Now this, you must note, this only applies to a polynomial, which is in the form ax to the n plus bx to the n minus 1 plus cx n minus 2, etc. Okay? So you need to note that. So the definition they give you here is essentially the formula for differentiating a term of a polynomial. And it says, if y equals ax to the n, you know what, actually, I'm going to write all of these important formulas, all of the ones you need to either, well actually they're going to be on your formula sheet, but all of the important differentiation formulas I'm going to do in purple so they stand out nicely. So, if y equals ax to the n, then dy by dx is equal to n(ax) to the n minus 1. So you see, you take the power down and multiply, and you decrease the power by 1. So that is our first rule of differentiation, or our first formula. Okay, and that is for polynomials. Okay, so you need to learn to understand these forms nicely and see when a function is a polynomial. And remember, a polynomial is ax to the n plus bx to the n minus 1 plus cx to the n. Okay, so, for example, let's do example 8 here. Example 8. They say, determine the gradient, so find gradient of, and remember, the derivative is the gradient, okay? So they say, find the gradient of y equals x squared, okay? So we know that the gradient equals dy by dx equals, okay, now, look at this. This here is in the form a x to the n, where a is 1, x is x, and n is 2. So, follow this. We put n in front, so we end up with 2, a is 1, x to the n minus 1. N is 2 minus 1 is 1. And there you go. There's your gradient. M equals 2x. Okay? Then I'm going to jump to example 10. So these are all examples of polynomials that we're differentiating. They say differentiate y equals root 3x squared. Okay, this means that y equals x to the 2 over 3, because this number on the root goes at the bottom of the power, the denominator of the power, and the power of the number goes at the numerator. Okay, so dy by dx, so now we're differentiating, is equal to, so how do we differentiate this? Well, do you see that this is once again in the form ax to the n? We've got a is 1, x is x, n is 2 over 3. So what do? We follow our rule. So dy by dx is n ax to the n minus 1. So n is 2 over 3, and we put it in front. So 2 over 3. Then we put a, which is 1. Then we put x. And then we put n minus 1 in the power. So 2 over 3 minus 1 is negative a third. And there you go. You've done your derivative. Okay. Alright, let's move on. Okay. So I'm going to do now example 12 quickly for you. Okay, and they say differentiate y equals 4x cubed plus 6x to the minus 2 minus 10. Okay. So, the first thing I want you to see is that this is in a polynomial form. Why? The form of a polynomial is ax to the n plus bx to the n minus 1 plus cx to the n minus 2, etc. Okay. So here we've got ax to the 3. This is constant x to the minus 2. And this is a constant. So, but remember, minus 10 is the same as minus 10 x to the 0. Do you see that? So it fits into this form, and it's a polynomial. Okay, so here we have a polynomial. Now, your book just jumps straight into differentiating it, which I don't like. I want to point out one of the differentiation rules, which your book will probably cover later because it's stupid. Right. One thing you need to know, because remember our differentiation rule that we spoke about earlier for polynomials. So for polynomials, we said ax to the n is equal to nax to the n minus 1. Nowhere did we ever talk about a differentiation rule. Well, sorry, d by dx of ax to the n. Okay, so the derivative of ax to the n is that. Nowhere did they ever tell you what the differentiation rule is for ax to the n plus bx to the n minus 1, etc. Okay, so what we're going to do is apply what they call the one of the properties of derivatives, and I'm going to do my properties in a lighter purple. So the property that we're going to use here is, and this is just a property that you need to know, d by dx, so the derivative, or dy by dx, of ax, or rather, the derivative of a function plus another function is equal to the derivative of a function plus the derivative of another function. So essentially what it's saying is that if there is a plus, okay, it's saying if, so this rule says that you can differentiate terms of an equation separately. That's what it's trying to tell you. So you've got, here is a term, here is a term, and here is a term. And what it says is, you see that, term plus term equals the derivative of a term plus the derivative of a term. So it says, this rule says, you can differentiate each term separately and then add the results afterwards. So let's differentiate it, because now we can differentiate this one by itself. Okay, and we know how to differentiate it because it's just follows that rule. This one by itself, which is also part of that rule, and this one by itself, also part of that rule. Okay. Actually, this one doesn't follow that rule. We'll get there. Right, let's start. So, dy by dx of, so m, the gradient equals dy by dx of 4x cubed plus 6x to the minus 2 minus 10, right? Okay. Now, from this rule over here, we know we can differentiate each term separately. So we can say that's equal to dy by dx of 4x cubed, okay, plus dy by dx of 6x to the minus 2 plus dy by dx of, last one is minus 10. Okay, so let's do it. Dy by dx of 4x cubed is, based on our polynomial rule, all you do is multiply, take the power down in front and multiply, so that is 12x, and we reduce the power, 12x squared, okay? Then we're going to go plus. And this is also a polynomial, it's also ax to the n, so we follow the same rule. And what do? We take the power down in front and multiply, so that gives minus 6 times 2 is 12, x to the minus 3, okay, because we reduce the power. And then our last one is, well, here's another rule for you, okay, dy by dx of c equals 0. The derivative of a constant is 0. Minus 10 is a constant, so plus 0. Okay, and there you go, you have your answer. You've done your derivative. 12x squared plus, or rather, minus 12x to the minus 3. There's your answer. Okay. One thing that I'd like to point out here is just a notation issue. Okay, very simple notation issue. Here you see we wrote m equals dy by dx of that. M, gradient of f of x. So if we say gradient of f of x, we can call that m, or we can say f prime of x, which means the derivative of x or the gradient of f of x. Derivative of f of x or gradient of f of x. That's what that prime means. So, m or f prime of x. So we can also say f prime of x equals dy by dx of blah blah blah. And then at the once we've derived everything, we're going to have f prime of x equals 12x squared minus 12x to the minus 3. There you go. Okay, so I think I'm going to call our video here, and in the next video I am going to cover hopefully most of this differentiation chapter. I'm going to cover it very quickly. There's a lot that needs to be done, but I'm gonna get through this differentiation chapter nice and quickly. Hopefully in the next video or the next 2 videos. Cool, Chase. Thanks a lot for watching, Cheers.